On a quiet Tuesday afternoon, at precisely 13 minutes to 1, a profound mechanical failure occurred within the Earth's crust. It manifested as a shallow magnitude 6.0 earthquake, with some agencies measuring it as high as 6.1, rupturing the floor of the southern Gulf of California. The epicenter was located northeast of La Paz, approximately 75 kilometers south-southwest of the coastal town of El Progreso on the Sinaloa side. For most observers, this was a minor regional event. The United States Geological Survey quickly assigned it a green alert, indicating a low probability of casualties or structural damage. There was no tsunami, no catastrophic wave, and no immediate emergency. By nightfall, the global news cycle had moved on, filing the event away as just another moderate offshore tremor. But this administrative dismissal misses the fundamental geological reality of the event. Plate boundaries do not recognize political cartography. The San Andreas Fault does not simply terminate at the Mexican border. It never has. Geologically, this offshore rupture occurred on the southern extension of the exact same tectonic boundary that runs directly beneath Los Angeles and under the feet of more than 20 million people in Southern California. The true story of this earthquake is not the minor shaking felt in northwestern Mexico, but rather the physical wiring that connects this active rupture site to a massive, locked fault system to the north. A system that scientific analysis reveals is now more dangerously loaded with tectonic stress than at any point in the last 1,000 years. The critical vector of this event lies in its physical metrics, starting with its depth. The rupture initiated only 10 kilometers down, roughly 6 miles beneath the seafloor. In geophysics, hypocentral depth dictates surface impact, while deep crustal ruptures must push their energy through kilometers of attenuating rock that scatters and dampens the shock waves. A shallow rupture at 10 kilometers delivers its kinetic energy to the surface virtually undiluted. On land, a shallow magnitude 6 is fully capable of collapsing infrastructure and causing widespread casualties. Here, disaster was averted not by the weakness of the source, but by a physical buffer of open water and geographical distance that bled off the highest amplitude seismic waves before they could impact populated coastal towns. This was no isolated, singular slip. Within a 24-hour window, the same segment of the Gulf was subjected to a violent cluster of successive ruptures. Alongside the main shock, seismographs recorded a secondary event near magnitude 6, a magnitude 5.3 out in the open Gulf, another magnitude 5.3 near El Progreso, and a magnitude 4.5 offshore of Topolobampo. This high-density sequence indicates a segment of the Earth's crust actively and violently reorganizing its internal structure. On a boundary defined by both shearing and rifting, such multi-shock bursts represent the sequential failure of adjacent minor faults, as tectonic strain seeks the path of least resistance. The energy was vast enough to register on high-sensitivity instruments thousands of kilometers away, including monitoring stations near San Diego, the central San Andreas Observatory at Parkfield, and even detection arrays in Japan. It was a physical demonstration that seismic energy ignores borders, propagating directly along the plate boundary. To comprehend the systemic threat, we must dismantle the conventional map of California's fault lines. The San Andreas is not a single, isolated line that ends in the desert sand. It is a critical component of a massive tectonic conveyor belt, accommodating the motion between two of the largest lithospheric plates on Earth, the Pacific Plate, grinding northwestward, and the North American Plate, retreating southeastward. They slide past each other at a relentless rate of 45 to 50 millimeters per year, approximately the speed of human fingernail growth. As this boundary enters the Gulf of California, the tectonic mechanics transition. Here, the plates are not merely sliding, they are pulling apart. This is the Gulf of California Rift, a young ocean basin in active formation, characterized by a staircase of short seafloor, spreading centers linked by long, violent transform faults where magma rises to form new crust and the rock snaps repeatedly under immense strain. The Gulf of California Rift, the Imperial Fault, the San Jacinto Fault, and the San Andreas are not isolated elements. They are structurally linked segments of a single continuous system. When the southern end of this machine shifts and releases stored elastic strain, that energy cannot simply vanish. It is redistributed along the plate boundary, altering the delicate balance of stress on the locked segments to the north. The absence of a tsunami in this offshore event is itself a diagnostic clue. Tsunamis are generated by vertical seafloor displacement on subduction zones. Transform boundaries, like those in the Gulf and the San Andreas, slide horizontally, leaving the water column largely undisturbed. This lack of a wave confirms that the Gulf of Cajon, the San Andreas, are the exact same species of geological beast. This brings us to the central question that geophysicists and emergency planners are forced to confront. Can a magnitude 6 earthquake at the southern terminal of this tectonic conveyor belt trigger the catastrophic rupture that Southern California has spent decades preparing for? While seismic waves from this specific event will decay too quickly to instantly snap the rock hundreds of kilometers away, the long-term mechanical implications are far more complex. Through the processes of dynamic triggering and static stress transfer, a distant rupture can act as a critical physical nudge. On a system that has quietly accumulated a millennium of strain, even the smallest incremental shift in stress can alter the equilibrium of a fault primed to fail. The southern San Andreas is wound tighter than at any time since the Middle Ages, and the structural limits of this system are being pushed to their absolute margin. How does a minor adjustment in the south reverberate through a heavily locked, thousand-year stress deficit to the north, and has the countdown to the inevitable reorganization of California's crust just been accelerated? To understand the gravity of this loading, we must first dismantle the alternative narratives that inevitably fill the information vacuum. In the hours following the Gulf rupture, theories proliferated across digital platforms, attributing the earthquake to government-operated ionospheric research facilities, solar flare cycles, or secret agencies withholding an imminent prediction of a larger event. The laws of physics easily dismiss these claims. The energy budget of a magnitude 6.0 earthquake dwarfs any artificial output by multiple orders of magnitude. There is no physical mechanism by which solar radiation can influence or release tectonic strain stored kilometers deep within the Earth's crust. Furthermore, geological agencies do not hide predictions. They openly publish their models, realizing that transparency is the only viable path to public safety. The real hazard requires no secret hand. The southern San Andreas and the adjacent San Jacinto faults are currently in a state of critical loading. Decades of satellite interferometry and GPS ground measurements tracking crustal deformation reveal that these faults have accumulated their highest levels of elastic stress in over 1,000 years. This is a physical measurement of ground displacement, not a statistical projection. The Pacific Plate has continued its relentless northwestward push, but because the fault planes remain locked by friction, that physical motion is converted into stored elastic energy. The system is a compressed spring wound tighter with every passing year. The last time this boundary held this much pent-up energy, the historical crusades had not yet begun. No modern city, aqueduct, highway, or dense population center has ever sat on top of a fault system in this state of load. We are the first generation to conduct this high-stakes experiment. The geological record exposes the severity of the deficit. The southernmost segment of the San Andreas, running through the Coachella Valley and down to the Salton Sea, has not experienced a major ruptures since approximately the year 1680. With a historical recurrence interval averaging between 180 and 250 years, this segment is now significantly overdue. Yet, while public attention is fixed on the San Andreas, seismologists are equally concerned by the San Jacinto fault. Branching off the main line is the San Jacinto is the most seismically active fault in Southern California. Cutting directly through the dense municipal sprawl of the Inland Empire, including Riverside, San Bernardino, and Hemet, the threat of the San Jacinto lies in its potential to act as a seismic starter. It converges with the San Andreas at a narrow mountain junction known as the Cajon Pass, a critical corridor carrying major rail lines, power grids, and aqueducts. Under typical stress conditions, the complex geometry of this junction acts as an earthquake gate, keeping the gate closed and stopping ruptures from jumping between systems. However, peer-reviewed modeling published in the journal Science Advances demonstrates that when both systems are critically loaded, the gate can swing open. A rupture initiating on the San Jacinto can breach Cajon Pass and jump directly onto the San Andreas, creating a massive multi-fault rupture. Because rupture length determines earthquake magnitude, such a joint failure scales the disaster exponentially. The mathematics of earthquake magnitude are unforgiving. Each step up the scale represents a 32-fold increase in energy release. A magnitude 8 earthquake releases roughly 1,000 times the energy of a magnitude 6. This exponential relationship is the basis for the federal shakeout planning scenario, which models a magnitude 7.8 rupture on the southern San Andreas. The projected impact includes 1,800 fatalities, 50,000 injuries, and $200 billion in economic damage, effectively severing Southern California from the national grid. The offshore event in the Gulf of California was not the trigger for this crisis, but it serves as a highly visible warning light on a deeply overloaded system. In the immediate aftermath of the Gulf of California rupture, the primary task of seismologists is to assess the short-term probability of a cascading sequence. The statistical reality of global seismicity is that approximately 90 to 95% of all earthquakes are standalone events that gradually decay into quiet aftershock sequences. Only a minor fraction, between 5 and 10%, turn out to be foreshocks that precede a larger, more destructive rupture. Therefore, the most probable outcome in the coming days is a quiet, predictable stabilization as the southern Gulf sequence settles down and its aftershocks fade along standard logarithmic decay curves. However, because the southern San Andreas system is currently sitting at its highest stress level in 10 centuries, scientists cannot afford to treat this event as a routine release of energy. Seismologists are now focusing their instruments on a specific geographic buffer zone, the Imperial Valley, located just north of the international border. The Imperial Valley has a well-documented history of responding to southern tremors. In past decades, strong earthquakes in the Gulf of California have repeatedly lit up the Imperial Valley with highly active swarms of smaller earthquakes within hours of the initial shock. If the Imperial Valley remains seismically quiet in the days ahead, it will indicate that this specific increment of transferred stress has been temporarily accommodated by the local crust. What would fundamentally alter this diagnostic picture is not subtle. The critical signal that researchers are actively watching for is a sustained climbing sequence of seismic events rather than a fading one. If we observe a pattern of migrating epicenters or a sudden burst of fresh energetic activity jumping northward from the Gulf into the Imperial Valley and the Salton Sea, the threat level changes instantly. These specific segments are the primary feeders that directly couple with the southern terminus of the San Andreas Fault. A cluster of tremors in the Salton Sea region represents the ultimate red line, as it places stress directly onto the locked Coachella Valley segment. The true significance of this Tuesday earthquake does not depend on whether a major disaster unfolds this week. This magnitude 6 event was not the trigger that broke the system, but it is a stark physical reminder of the boundary's structural continuity. The entire region, stretching from the spreading rifts of the Gulf of California through the Imperial Fault, up into the San Jacinto, along the San Andreas, and through the structural bottleneck of the Cajon Pass, is one single, connected, critically loaded machine. This machine is actively running, grinding, and accumulating elastic strain beneath one of the most densely populated and economically vital regions in North America. When dealing with a system of this scale, the correct scientific and practical response is not panic, but systematic preparation. The geological evidence collected over decades is unambiguous. The southern San Andreas will rupture again. This is not a speculative hypothesis, but a structural certainty dictated by the continuous 45 to 50 millimeters of annual plate motion that must eventually be released. Seismologists and structural engineers have stated plainly that Southern California is not prepared for the inevitable regional reorganization of its crust. The value of this moderate offshore earthquake is that it acts as a highly visible warning light, pointing directly at the critically stressed machine to the north, while the window for mitigation and reinforcement remains open. The Gulf of California did not pull the trigger this time, but it has forcefully reminded us that the weapon is loaded and the only remaining uncertainty is the exact moment the system reaches its breaking point. The physics of stress redistribution operate at both the macroscopic scale of continental plates and the microscopic scale of fault plane friction. To trace how a rupture in the Gulf of California interacts with the northern segments under Los Angeles, we must examine the two primary modes of stress propagation: dynamic triggering and static stress transfer. Dynamic triggering occurs in real time as transient seismic waves radiate outward from an epicenter. When these high-frequency vibrations pass through a distant fault zone, they act as a rapid physical disturbance. If the rock is already near its shear strength limit, the momentary pressure change from these passing waves can act as the final decisive nudge. This is not a hypothetical model, it is a documented physical phenomenon. The 1992 Landers earthquake, a magnitude 7.3 event, famously triggered sudden bursts of seismic activity at vast distances far beyond its zone of direct destructive shaking. Historically, the Imperial Valley has repeatedly experienced immediate swarms of minor earthquakes directly following major ruptures in the Gulf, proving the high sensitivity of this interconnected system. While dynamic triggering is a rapid, transient effect, static stress transfer is a permanent structural modification of the crust. When a fault segment slips, it relieves tension locally, but that displacement physically pushes the adjacent rock at the tips of the rupture, transferring the load further down the line. It is a simple conservation of stress within a closed mechanical chain. By releasing strain in the southern Gulf, the tectonic conveyor belt shifts a portion of that load northward. On a relaxed system, this minor increment would be negligible. But on a fault network that is currently carrying its heaviest load in 1,000 years, even a minor addition of static stress brings the system closer to its mechanical shear limit. This structural strain converges on the most vulnerable bottleneck in the Southern California grid, the Cajon Pass. Situated north of San Bernardino, this narrow pass is a critical junction where the San Andreas and San Jacinto faults run in close proximity. Under normal tectonic conditions, the complex geometry of this junction acts as an architectural barrier, a closed gate that prevents a rupture on one fault from crossing over to the other. But when both systems are critically loaded, the geomechanical barrier degrades. Peer-reviewed modeling published in 2016 in the journal Science Advances analyzed this exact hazard, reconstructing a historical earthquake from the year 1812. The study confirmed that the Cajon Pass gate had indeed swung open, allowing a single, massive rupture to tear through both the San Jacinto and San Andreas faults simultaneously. The consequences of a dual fault cascade of this nature are dictated by the absolute mathematics of earthquake energy. Because the physical length of a rupture is the primary variable determining an earthquake's magnitude, allowing a rupture to breach the Cajon Pass gate and propagate across both systems turns a serious localized event into a regional catastrophe. The United States Geological Survey modeled these exact dynamics in its shakeout scenario, projecting a magnitude 7.8 rupture along the southern San Andreas. The resulting metrics represent a profound systemic shock. Approximately 1,800 fatalities, 50,000 physical injuries, and up to $200 billion in immediate economic losses. The model demonstrates that the vital utility and transportation lifelines crossing this zone would be immediately severed. The moderate magnitude 6.0 rupture in the Gulf of California did not initiate this catastrophic cascade. But in the cold logic of geophysics, it served as a diagnostic test of a highly pressurized machine. The geological record, the historical recurrence interval, and the modern satellite measurements of millennial-scale strain accumulation all point to the same conclusion. The system is operating at its structural limit. The question confronting the region is not if the southern San Andreas will fail, but how the integrated infrastructure of 20 million people will respond when the loaded machine finally releases its stored energy. We must address the human element of this crisis, specifically the unprecedented nature of our modern vulnerability. When the southernmost segment of the San Andreas Fault last ruptured in approximately the year 1680, the surrounding region was an unpopulated desert basin. Today, that exact same fault line is overlaid by a dense network of high-voltage power lines, fiber optic communication cables, major aqueducts supplying water to millions of residents, and highly integrated municipal infrastructure. The system is operating under a structural load it has never experienced in the presence of human civilization. We have built our complex, fragile societies directly on top of a giant mechanical spring that has been quietly compressing for more than 3 centuries. No modern city, highway, or population center has ever sat on top of these faults in a state this loaded. We are all of us the first to test these limits. To analyze this hazard with scientific rigor, we must discard the superficial myths that regularly distort public understanding of seismic events. In the immediate aftermath of any significant earthquake, alternative narratives inevitably circulate, claiming that the rupture was artificially induced by secret government research programs or triggered by recent solar flares. The physical laws governing tectonic energy budgets instantly expose these claims as impossible. A magnitude 6 earthquake releases an immense amount of energy, a quantity that completely dwarfs any electromagnetic or physical stimulus that a human facility could ever inject into the Earth's crust by many orders of magnitude. Furthermore, there is no known physical mechanism by which solar flares can interact with or release tectonic strain stored miles beneath the surface in solid rock. Far from hiding these worst-case scenarios, the Geological Survey publishes these models openly. The true danger requires no secret hand. It is simply a natural plate boundary, doing exactly what plate boundaries do on a network that has quietly wound itself to a 1,000-year breaking point. This leaves us with the immediate, empirical task of monitoring the boundary's response. Seismologists are currently analyzing the seismic data coming out of the Imperial Valley, looking for the presence or absence of triggered earthquake swarms. If the Imperial Valley remains stable and the aftershocks in the Gulf of California continue to decline along a normal decay curve, then this specific chapter of tectonic readjustment will draw to a quiet close. But the underlying crisis will not have been resolved. What would change this picture is not subtle. A sustained climbing sequence of seismic activity jumping north to the Imperial Valley and the Salton Sea onto the segments that actually feed the San Andreas is the critical signal worth watching for. The real value of the Gulf of California earthquake is that it acts as a stark empirical warning light, pointing at the machine to the north while there is still time to look. It has demonstrated that the tectonic conveyor belt is active, connected, and highly dynamic. In the cold, objective language of geophysical analysis, the system has reached its structural limits. The strain accumulated over centuries has created a profound deficit that must eventually be balanced by a physical reorganization of the crust. The southern San Andreas will rupture again. This is an absolute certainty dictated by the continuous 45 to 50 millimeters of annual plate motion. The true boundary of our safety is not defined by a date on a calendar, but by the physical capacity of our infrastructure to withstand the inevitable release of this millennial-scale energy. The correct response is preparation, not panic. This recent offshore event was not the trigger